Hi everyone, and welcome back to this series of solving questions from the exam ELC A5. And this exam is for the passing of the technical exam of the PEng, Professional Engineering Exam in Ontario and other provinces in Canada. Today I will try to cover an important topic in non-ideal op-amps, which is the slew rate. So first, I would like to explain what is the slew rate. What is the impact of the slew rate on your output of the op-amp, why it's happening in a very short explanation. Then we will have one of the exam problems to demonstrate to you how we can apply this in exam problems. So basically, the slew rate is the ability of the output signal to follow the input signal, okay, or the inability of the output signal to follow the input signal. Now, for example, if I have a step function with zero rise time, and if I connect that as the input for this voltage follower for an ideal op-amp, your output will be exactly matching the input. But because of this slew rate, which is basically volt per microsecond, how much the signal in the output can follow the your input, you will have basically either an exponential function if omega t, which is the bandwidth of your op-amp, times the voltage is less than or equal to the slew rate. If this conditions satisfied, then the output, if you have a step function, it will follow basically an exponential function. However, if the omega t times v is more than the slew rate, then it will follow a linear rise time, as you see here in this figure. Okay, so that is as simple as what is the slew rate of the op-amp. Now let's see the question here. This question happens to come in the exam of May 2015 and December 2019. Here we have an op-amp with the slew rate. So this is something you have to, once you see this, you know that this is non-ideal op-amp and you have to consider the slew rate. With a unity gain bandwidth, with the unity gain, so this is basically a voltage follower. The bandwidth is 1 megahertz of your op-amp, is connected as a unity voltage follower configuration. What is the largest possible input voltage step for which the output voltage can still produce an exponentially rise and fall waveform? So basically, you want to see what is the maximum voltage that your V out will be following this formula. So so the condition I just mentioned in the previous slide, which is omega t times the voltage, should be less than or equal to the slew rate. Or your voltage should be less than or equal to the slew rate divided by omega t. Now the slew rate here is 1 volt per microsecond divided by omega t, which is 2 pi times ft, which is 10 to the power 6. Now we need to convert the microsecond to seconds, so I need to multiply to 10 to the power of 6. So you will have basically 1 over 2 pi, which is 0.16 volt. So if my voltage is less than or equal to 0.16, the output voltage will follow this relationship. Part B says here, for this input voltage, which is the one that is we found here, or less than that, meaning that you are following the exponential function, find the 10% to 90% rise time. A bit of background, if I have here a rise function like this, so this is your eventual value, this is your V out, the steady state, okay? Now, we have here T1 and T2. In T1, basically, you reach 0.1 of this V out, and in T2, you reach the 0.9 of V out. The difference between T2 minus T1 is basically your rise time. So we need to find T1 and T2, and then take the difference, and with this, we will be able to find our rise time. Okay, so the function here, because we are talking about a voltage less than or equal to the 0.16 volts. So your V would equal to, your V output will equal to your V, the input voltage, 1 minus E minus omega t times t. The unknown here is the time. Now, your output voltage will be equal to 0.1 of that voltage. Whatever the voltage your will be, like 0.16, 0.1, as far as it is 0.16, it is 0.1 volt equal to V times 1 minus E minus omega t times t. The V will cancel here, okay? So you will have e to the minus of omega t of t will equal to 1 minus 0.1 or 0.9. Take the ln for both sides. So we have ln e minus omega t of t equal to ln of 0.9. Ln of 0.9 is nothing but equal to minus 0.10536, which is equal to ln of the E, you will get this, is equal to minus omega t times t. The minus will cancel, and your t will equal to 0.10536 divided by 2 pi f of t, which is 10 to the power 6, the 1 megahertz, and you will do the calculations, you will get this is equal to 0.0167 microseconds. So this is the rise time. This is how long it will take your signal to reach 0.1 of the maximum output voltage. We will repeat the same thing, but now at 0.9, which is 0.9 V equal to V 1 minus E minus omega t times t. Exactly the same thing here. So you will have e to the minus omega t of t is equal to now 0.1. Take ln of both sides. So we'll have ln of e minus omega t of t, which will equal to minus omega t t equal to ln of 0.1, okay, which is equal to minus 2.3025 8, and from this you can find your t, which is will equal to 0.36647 microsecond. So this is your t2, this is your t1. We found both of them now. So the rise time tr will equal to 0.36647 minus 0.0167, which is equal to 0.35 microsecond. This is basically your rise time. Now, in part C, if the input step is 10 times larger than the voltage that we have found in A, find the rise time between 10 to 90%. Now, in this part, the signal does not follow anymore the exponential, but is a linear function like this. And this linear function, this is the slow rate. I know it. This is 1 V per microsecond. This is the time. This is the voltage. So this is your slope. Okay, so now becomes even a simpler problem. So this is your T1. This is your T2. So this is your 0.1 times the voltage, which is 10 times, which is 16 volts. So this would be equal to times 16, sorry, 1.6, because the voltage we found was 0.16, so 10 times that is 1.6, and here it is 0.9 times 1.6. So that is the slope. So your slope, which is 1 volt per microsecond, will equal to the differences of y divided by the differences in x. So this will equal to 0.9 times the 1.6 minus 0.1 times the 1.6 divided by T2 minus T1. T2 minus T1 is TR, your rise time. That is what I want to find. So this is equal to TR. So your TR basically will equal to 0.9 times 1.6 minus 0.1 times 1.6 divided by 1 volt per microsecond, and this will give me a total rise time of 1.28 microsecond. So with this, now we know how to handle a question that has a slow rate in the op-amp.